So tangent planes make wonderful approximations to our surfaces. And that's because locally, when we zoom in really close to a surface, it looks flat. We're like, well, that's great. Can we do better? In other words, can we improve our approximation? And so we might say, well, what do you mean by improve the approximation? Well, it says so that as we look nearby, it's even better than just a tangent plane. Well, we say, we've done stuff like that before, right? Yeah. If you think back to one of the things we did in Calculus 2, there was this notion of Taylor polynomials. And so what we want to do is say, can we do something for multivariable functions? And the answer is yes. Let's begin. So, as we said, when our partial derivatives exist, we have our function is a tangent plane. So this part right here, this is our tangent plane, but it's not perfect. So what you get is it's the tangent plane plus an error term. And essentially, the error term is how far off are you? Now, it depends on several things. Generally speaking, when we are close to the point AB, the error term is small. Nevertheless, what we'd like to do is say, how can we make a better approximation? How can we make our error get tinier? So, let's go back to single variable calculus, because that's oftentimes the way we build up our intuition. And when we were in single variable calculus, we said, okay, we can talk about our Taylor polynomial, which here's the basic idea. What we want to do is we want to get better, and we do it by getting more approximations to our derivatives. All right, so what can we say? Well, we could say, for example, our function is the value at a plus a huge error. Now, what is that saying? Well, what we have, okay, let's sketch ourselves a curve to get some intuition going. So if we have a curve, let's draw one in. Then I could say, what's happening at a particular point? Well, if I say, look, I can approximate it by saying, let me just see what the value of the function is at that point. That would be one approximation. Now you can see, not the best one. Well, the next level is to go to our tangent line. So if you look here, the f of a plus f prime of a times x minus a is the tangent line. And so it says, look, think about it as approximating it with a line. And what do you see? Well, the line does a better job than the horizontal thing. In other words, it's a better approximation over a larger range. But it's not perfect. It still has problems. But notice what happens to our error. It started to shrink, which means as we look nearby, our error is less than it was before. Well, how do we go even further? And now the idea says, oh, the tangent line matches the function and the derivative, so to get further, we'll match the function, the first derivative, and the second derivative. So that's the idea of Taylor polynomials. Match derivatives. And so the second order Taylor polynomial, which is as far as we need to talk about, says make it a parabola. So it's a parabola, and nearby it looks something like that. And the nice thing is the parabola is an even better estimate. So the philosophy says the more derivatives that we match, the more closely we're mimicking the behavior of the function nearby. In other words, we're doing a better job of approximation. So that's the whole idea, is like, okay, Taylor polynomials, match derivatives, we can understand behavior. Cool. Now, how do we go up into multivariable functions? Well, the idea is, okay, so now instead of focusing on matching derivatives, we'll do it for partial derivatives and up to some order. So we can think about, in our case, our second order Taylor polynomial. Well, what do we want to do? We want to match the function. So that's the value of the function AB. You can think of that as the 0th derivative. We want to match the first derivative, so that's f sub x ab, f sub y at ab, and then we times by x minus a and y minus b respectively. And notice if we stop here, this part right here is called tangent plane. So you can think of as a similar thing, the tangent plane is a Taylor polynomial, just like the tangent line is a Taylor polynomial. But now we're going to push a little bit further. So we're going to also match the second order derivatives. So we have 1/2 fxx ab times x minus a squared, fxy at ab times x minus a y minus b, 1/2 fyy ab times y minus b squared. And that is the second order Taylor polynomial. Now, you might ask, where are all these pieces coming from, and why are we claiming that these are matching? Well, let's just take an example. Suppose we plug in a, b, right? So we're going to plug in x equals a, y equals b. Over here, we'd get f of a, b. Now notice, because I plug in x equals a, anything with an x minus a goes away. Because I plug in y equals b, anything with a y minus b goes away. So the only thing left is ab. So that's what we mean when it says the value matches there. Now let's suppose we take a derivative with respect to x. Well, if we take a derivative with respect to x on the left-hand side, what we get is that fx of xy, well, is approximately, well, there's no x involved. That's the constant, goes away. Here, there's a single x minus a term, so that would be fx at ab. There's no x there, so that doesn't go away. Here, well, there is an x minus a squared. When you take the derivative, the 2 comes down. Aha, there's a half there, so that would be plus fxx at ab times x minus a. Here, it's just the derivative of x minus a, so that's plus fxy at ab times y minus b. And here, there's no x at all, so that just goes away, goes to 0. And now notice, if you plug in again, x equals a, y equals b, the x equals a knocks out the term with the fxx, y equals b knocks out the term with the fxy, and so you're left with fxab. In other words, the derivative matches. So f sub x is what it should be. What if we went even further? Now, we could imagine doing two things. If we took the derivative with respect to x now, we can see fxx, well, the only term left would be this fxx at ab. So we'd have the fxx at ab matching. If we took the derivative with respect to y, the only thing left would be this term. So the fxy term would match as well. Aha! It's all matching. And so that's what we have. And so it's a very simple idea. The reason we need the half is because when we take derivatives with the 2, it comes down, right? So we need to have the half to compensate. That's the reason we have to have a half. The reason this doesn't have a half in the fxy, well, we don't need to compensate for any large exponent. So there's no real surprises. So key idea, if you just remember the following, it gets you pretty much 95% of the way there. Of course, the 5% is the details, and there's lots of details. And so the key idea is that the derivatives match up to some order. All right, now, great. Why do we care? That's a good question. Why do we want to know about our Taylor polynomials? Well, in particular, I'm going to say we want to focus a lot of energy onto what happens if our tangent plane is flat. Okay? So what does it mean to be a flat tangent plane? Well, it means we're not changing the x or y direction. And so, if we have a flat tangent plane, these are equal 0. because our partial f partial x is 0 and partial f partial y is 0. So this equals 0 when our tangent plane is flat. So if we want to know what's happening when we have a flat tangent plane, our answer is, aha, we go further down and we look here. So this part is going to drive our behavior. So in other words, if I want to know what's happening when I have a flat tangent plane, the second derivatives are going to tell me what's happening. So that's why we want to spend some time digging into what's happening here. So we're going to take some detours, and I want to say that the main takeaways for right now are this key idea. So know how to take a second order Taylor polynomial, remember that derivatives match, and you'll be mostly good. A lot of what we're going to talk about in the next 10 minutes or so is important information, but we're going to be able to succinctly wrap it up and say, aha, here's this beautiful fact, and we're just going to take it as is and use it. So if the next few minutes sounds a little like out there, it's okay, just hang on. We'll come back. We're going to talk about briefly something that we call the quadratic form. Quadratic, you should just think of like a second order polynomial. And we're going to push into, remember we said we really care about the second derivatives. They're going to tell us what's happening locally. So if we think about what's happening with our second derivatives, it turns out we can write it in a rather nice way. So our 1/2 fxx delta x squared plus fxy delta x delta y fyy times 1/2 delta y squared. And by the way, the delta x delta y, delta x just means change in a, so that's x minus a. Delta y, change in b, that's y minus b. We can rewrite it as 1/2 times a vector, delta x delta y, times this nice little 2 by 2 matrix, times another vector on the other side, delta x delta y. And if you unravel the matrix multiplication, so in other words, you multiply this matrix by that vector, multiply two vectors together, expand it all out, you get back to here. That's not important. If you can try it out by your own, it's very straightforward. So we say, okay, this part right here, this little 2 by 2 matrix is important. If our gradient is 0, which is going back to a flat tangent plane, f sub x equals 0, f sub y equals 0, then that little 2 by 2 matrix really determines everything. And there's this really cool fact. Again, outside the scope of our class, this would get more into what's called linear algebra, which is a beautiful subject. You should take it if you can. It'll really help you appreciate calculus. And it's a wonderful subject. But it's this really cool thing. It says, hey, it turns out that if you have a nice little 2 by 2 matrix here, that there's two special numbers. We call them lambda 1, lambda 2, and they're called eigenvalues. And they have the following property. This can be written as this first eigenvalue times a square involving some combination delta x and delta y, and then there's a lambda 2 times another square combination delta x, delta y. Now, if you're familiar with what are called eigenvectors, you might say, well, where are the eigenvectors showing up? Well, they're showing up in the alpha, beta, and the gamma and delta. If you don't know what an eigenvector is, again, don't worry. But the important thing here is we say, aha, this form here, quadratic form, is some combination of two squares. And the nice thing about squares is that they're always greater than or equal to 0. So we say, lambda 1 and lambda 2 are important. If we know what's happening with lambda 1 and lambda 2, we know the whole game, and we win. So, what are some possibilities? Well, let's run through them. if lambda 1 and lambda 2 are positive. Well, what does that say? Well, if we scroll back here, if lambda 1 and lambda 2 are both positive, everything goes up because everything is greater than 0. So what we look like is we look like a bowl. So lambda 1 and lambda 2 being positive says we have that type of shape. Locally, we're coming up. So if our function was our tangent, if we have our flat tangent plane to our function is coming up as a bowl above. All right. If they're both negative, well, again, we can look back here. Then this will be net result less than or equal to 0. This will be less than or equal to 0, which means we're going to be going down. So our shape is an upside down bowl. So we look something more like that. And again, our intuition says, oh, if we have our flat tangent plane to our function, we're going to be saying our function is going to be coming down below our tangent plane. What happens if one is positive and one is negative? Well, this is where things get interesting. What happens is in that some directions you go, you're going to be coming up, but in other directions you go, you could be going down. And so it's neither going above or below, it's doing both, just depending upon which way you go. And that has a very nice shape. We call it a saddle. You might be saying, boy, this feels really reminiscent of when we talked about quadratic surfaces. Well, there's a reason we talked about quadratic surfaces. It's so that we could talk about what's happening here. So a saddle, as you hopefully recall, is a shape. It has sort of a saddle-like appearance, which is why we call it a saddle. In one direction, we're going up, and in another direction, we're going down. Okay, well, what happens if one of these numbers, lambda 1 and lambda 2, is 0? Well, great question, and the answer is not enough information, and we don't know. We'd have to push deeper into higher order derivatives or take a closer look at the function, but the good news is, for our purposes, we're not going to worry about that. So you might say, okay, so we want these numbers lambda 1, lambda 2. We're going to actually not care about the values. We want to know about the signs, whether they're both positive or they're both negative. So there's one last thing we need to talk about, and it's the following. Namely, if I have this little matrix A times A, B, B, C, then you might recall something called the determinant. We talked about that when we talked about finding cross products. C. The way you take the determinant is for 2 by 2, you take the diagonal going down, so that would be A times C, subtract diagonal going up, B times B, B squared. Well, it turns out that this quantity is also equal to the two numbers we're interested in multiplied together. So if we look at AC minus B squared, we can at least answer the question, do things have the same sign or do they have different signs? If this quantity is positive, then lambda 1 and lambda 2 both have to be the same sign. So it either says, oh, I look like a bowl going up locally, or I look like a bowl going down locally. If they have different signs, it says, oh, I have to look like a saddle. I have some directions I go up, I have other directions where I go down. And so we're going to use this fact here because we're only interested in the behavior qualitatively, which is determined by the sign, not quantitatively, which is determined by the magnitude of the terms. Now, we're going to put all this into context when we start talking about a classification. So this is helping set ourselves up to understand how to classify locally what surfaces are. But for the main purpose for today, remember it's about Taylor polynomials. The idea is match the derivatives up to some order. That's the whole idea. Now we talked about what if I have a function of two variables and I match up through the second derivative? But you could say, well, can I do more? For example, can I do it with a function of three variables and match up through the second derivative? And the answer is yes, you can. And well, there's a lot of terms, and you just have to be patient. So for example, you have the function, the first derivatives, so the gx, gy, dz, and you have all the second derivatives. And even though there's really 9 second derivatives, we can collapse it into 6, right? Because we have gxy is the same as gyx. If you think about it, it kind of gets you into the mindset like, oh, so that's what was happening. So if we go back a couple here, you might say, well, where is the fyx? Well, you can think of, oh, they're really both there. fxy is the same as fyx. So if you think of them as each getting a contribution of a half, everybody got the same amount of a contribution. Okay. You don't need to memorize this formula. You just need to know it's possible. And in fact, it's better not to memorize the formula. It's better to memorize the principle. The principle is match all the derivatives up through a certain order. But okay, if we can do it for functions of 3 variables up to second order, can we do, say, a function of 2 variables up through a third order? Yes, we can do that as well. Not surprising. It's a little bit long, but okay. You match the 0th derivative, the first derivative, the second derivative, and then you push into the third derivatives. And there's a lot of third derivatives, but it turns out that really there's 4 up to symmetry. And so you get 1/6 fxxx, 1/2 fxxy, 1/2 fxyy, 1/6 fyyyy. And you might say, where does the 1/6 come from? Does that make sense? Think about derivatives. When I take the first derivative, the 3 will come down. The next time I take a derivative, the 2 will come down. That means I have a 3 times a 2, and then if I take one more times a 1, 3 times 2 times 1 is 6, so the 1/6 is to compensate. Here when I take derivatives, I'm going to have to bring the 2 down, but then it'll be a 1, here it'll be a 1, so I have a 2, a 1, and a 1. So I need a 1/2 to compensate. So those are where those numbers are coming from. It's actually not so bad when we look at it, and life is good. But again, this is something else that we don't need to memorize. I just want to show you it is possible. It does exist. Remember the principles. The principle is Taylor polynomials, we match up through a certain order. And for us, we're really going to focus on second order. That's the most important thing. All right, well, time for some practice.